Pluto, a distant and modestly sized planet, was once a singular member of our solar system's planetary family. However, startling announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a staggering revelation. They propose that this cold world is on a potential collision course with Neptune. But how could this happen, and what might be the consequences of such a massive event? Are we witnessing a fascinating cosmic phenomenon, or is there more to this impending celestial collision? Join us as we explore the potential consequences of a Pluto-Neptune crash. Pluto, once considered a planet but downgraded to a dwarf planet due to its peculiar orbit, remains a subject of interest and study within the cosmic community. According to recent predictions by leading scientists, Pluto's trajectory is alarmingly close to Neptune's. Both Neil deGrasse Tyson and Michio Kaku have raised warnings about a potentially dangerous collision between these two celestial bodies, a collision that could pose a massive threat to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit. This means that since its discovery in 1930, Pluto has not even completed one full revolution around the Sun. However, the intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating greatly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unusual is its inclination, measured at 17 degrees to the ecliptic plane. This steep angle, combined with its eccentricity, adds layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its interaction with Neptune's. For about 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, contrary to what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to grasp its unique path. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stood out with its steep inclination and eccentric shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit amidst these complexities is a testament to the intricacies of celestial mechanics. The three-body problem in space involves predicting how three objects, like Pluto, Neptune, and the Sun, move and influence each other through gravity. It's like trying to forecast their future positions based on where they start and how they pull on one another. In Pluto's case, this problem demonstrates how its path, Neptune's path, and the Sun's gravity all interact in a complicated manner. Terms like asymptotic libration and degree libration, along with the VZK oscillation, are part of this puzzle. According to astrophysicists, these phenomena are key to understanding why Pluto and Neptune avoid collision. At any point when Pluto crosses Neptune's orbit, their positions are always at least 90 degrees apart. This spatial separation is crucial in preventing their orbits from overlapping. Similarly, vertical libration refers to the upward motion of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, providing an additional layer of safety from potential impacts. Another critical factor is the VZK oscillation, named after three scientists who studied how objects move in space. This concept explains how Pluto, Neptune, and the Sun's gravitational pulls interact. Despite the apparent chaos, this oscillation helps maintain Pluto's orbit over incredibly long periods. These factors illustrate how, despite initial appearances, the cosmos operates under intricate patterns and rules that keep everything in order. The stability of Pluto's orbit demonstrates the fine balance achieved through the interplay of gravitational forces and orbital mechanics. In the 1980s, numerical simulations revealed that Pluto's orbit, though stable over long periods, is inherently chaotic. Minor variations in initial conditions can lead to massive differences over thousands of years. Nevertheless, these chaotic properties are balanced by mechanisms like Neptune's gravitational resonance with Pluto. For every 3 orbits Neptune completes around the Sun, Pluto completes 2, a resonance that stabilizes their relationship. Jupiter's gravity also plays a significant role in safeguarding Pluto's orbit. Along with Saturn, these giant planets contribute to maintaining the stability of Pluto's path over billions of years. It seems that Neptune, Jupiter, and Saturn work in harmony to ensure Pluto remains on a safe course without veering into trouble. Understanding these dynamics is crucial for grasping the broader structure of the solar system. Without such mechanisms, celestial bodies like Pluto could collide with others or be ejected from their stable orbits, leading to a chain reaction of disruptions. The study of Pluto's orbit also highlights the limitations of our predictive capabilities. While computer simulations have advanced our understanding, the inherent chaos in systems like Pluto's orbit reminds us of the ever-changing nature of the universe. Despite this unpredictability, Pluto's orbit demonstrates that even seemingly unstable paths can achieve balance through the complex interaction of gravitational forces. This delicate balance in Pluto's orbit not only underscores the intricacies of celestial mechanics, but also highlights the resilience of the solar system. The synchronized interplay of gravitational forces ensures that even chaotic systems maintain stability over vast timescales. However, understanding these dynamics requires constant observation and advanced computational tools. Astrophysicists have used sophisticated models and simulations to deepen their understanding of Pluto's orbital behavior. These simulations rely on highly precise mathematical equations to replicate the gravitational interactions between Pluto, Neptune, and other bodies in the solar system. By tweaking initial parameters, such as position, velocity, or gravitational constants, researchers can predict how small changes might affect the long-term stability of Pluto's orbit. Interestingly, these studies reveal that while Pluto's orbit can appear chaotic in the short term, it operates under a broader framework of order over billions of years. This phenomenon, often referred to as bounded chaos, explains how small instabilities coexist with large-scale stability. Implications for future collisions. Although the mechanisms protecting Pluto and Neptune from collision are well understood, they are not infallible. Over extremely long timescales, on the order of millions or billions of years, subtle perturbations from external forces, such as passing stars or interstellar objects, could alter the gravitational dynamics of the solar system. Such changes might disrupt the delicate balance that keeps Pluto's orbit safe. Moreover, the study of Pluto and Neptune's orbits provides a window into the dynamics of exoplanetary systems. By understanding how our solar system avoids catastrophic collisions, scientists can apply similar principles to study distant star systems, where gravitational interactions are even more complex. Broader significance. Pluto's orbit is not just a curiosity. It's a case study in the stability and resilience of the cosmos. The gravitational relationships that govern its movements serve as a microcosm of the forces shaping the universe. These forces demonstrate how chaos and order coexist, creating a dynamic yet predictable system. Furthermore, Pluto's story reminds us of the importance of interdisciplinary collaboration in science. Astronomers, mathematicians, and physicists have worked together to unravel the mysteries of its orbit, blending observational data with theoretical models. This collaborative approach has enriched our understanding of the solar system and expanded our knowledge of orbital mechanics. Conclusion. Pluto's journey around the Sun is a testament to the complexity and beauty of the universe. Its peculiar orbit, once seen as an anomaly, now offers profound insights into the stability of celestial systems. Through the interplay of gravitational forces and orbital mechanics, Pluto's path remains stable despite its chaotic tendencies. As we continue to explore the solar system and beyond, the lessons learned from Pluto will guide our understanding of celestial dynamics. These discoveries remind us that even in the vastness of space, order and predictability often emerge from chaos, offering a glimpse into the harmonious workings of the cosmos. Let me know if you'd like to expand on any specific aspect or if there's a particular angle you'd like me to focus on. Impacting the security and direction of different bodies inside the framework. So for what reason are unmistakable astrophysicists just now raising worries about an expected accident among Pluto and Neptune? In spite of this multitude of complicated forces attempting to keep such an event from happening, Neil deGrasse Tyson, a famous astrophysicist, offers an exceptional perspective on the mysteries of our solar system, especially the captivating case of Pluto. Tyson, known for his role in the renaming of Pluto from a planet to a dwarf planet, offers insightful commentary on the evolving nature of celestial mechanics and the public's fascination with the uncharted reaches of space. Tyson's stance on Pluto's renaming is rooted in the ever-expanding knowledge of our solar system. He considers the renaming not a demotion but rather a necessary adjustment to our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He observes the complexities of Pluto's orbit and its interactions with Neptune through a lens that acknowledges the unpredictability of space. He suggests that while Pluto's orbit is stable for now, it could undergo significant changes in the future. This possibility serves as a reminder of how much we still need to discover about the forces shaping our solar system. All in all, Pluto's orbit is a fascinating case study of the intricate interplay of gravitational forces in the solar system. While its path is stable at present, the complex dynamics between Pluto, Neptune, and other planets imply that even the most seemingly stable orbits could change over time. As astrophysicists like Neil deGrasse Tyson continue to explore the mysteries of the universe, they help us better understand the delicate balance governing the movements of celestial bodies. The potential for a Pluto-Neptune collision isn't necessarily imminent, but it's a reminder of the constantly evolving and unpredictable nature of the universe. Notwithstanding the scientific theories surrounding Pluto's orbit, it's vital to consider the broader implications of these dynamics for our understanding of the solar system and the universe at large. While Pluto's journey is one of intrigue, it also reminds us that the universe is full of hidden complexities waiting to be explored. The concept of orbital resonance, particularly between Pluto and Neptune, is a critical piece of the puzzle. This resonance, where the ratio of Pluto and Neptune's orbits is 2:3, is a remarkable feature of celestial mechanics. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This ratio ensures that, although the orbits cross, the 2 planets never collide. This is due to the gravitational interactions that stabilize their paths, working in tandem to prevent any catastrophic collision. The importance of resonance in maintaining cosmic stability cannot be overstated. It illustrates how systems in space, even those that initially appear chaotic, can self-regulate through subtle gravitational forces. Understanding this resonance also explains why Pluto, despite its erratic orbit, has remained stable for billions of years. This phenomenon is a fundamental aspect of the solar system's larger architecture. The effects of planets like Jupiter, Saturn, and even Uranus are crucial in maintaining stability in the orbits of smaller bodies like Pluto. Jupiter, with its immense gravitational power, acts as a kind of protector for the inner solar system, influencing the trajectories of various asteroids and other dwarf planets, including Pluto. In fact, some experts speculate that Jupiter's gravity may have prevented Pluto from being ejected from the solar system entirely. Without Jupiter's protective influence, Pluto's orbit could have been disrupted far more significantly, potentially sending it out of the Sun's gravitational influence. Furthermore, the concept of gravitational perturbations comes into play over long periods. The orbits of planets and dwarf planets are subject to subtle shifts due to the gravitational pull exerted by neighboring objects. While Pluto's orbit may seem relatively stable now, the positions of Neptune and other giant planets can influence its movement, causing small deviations over time. These perturbations are part of a broader mechanism that drives the evolution of orbits throughout the solar system. Astronomers use sophisticated simulations to track these movements, predicting how objects like Pluto could evolve in the future. These models allow scientists to explore various scenarios, accounting for factors such as gravitational interactions and initial orbital conditions. Another crucial aspect to consider is the role of observational technology in understanding these phenomena. The study of distant objects like Pluto has only been possible thanks to advancements in telescopic technology. With the launch of the New Horizons mission in 2015, humanity was able to gather unprecedented data about Pluto, including its surface features, atmospheric conditions, and interactions with the solar wind. This data has been instrumental in refining our understanding of Pluto's orbit and its potential future developments. As telescopes continue to improve and more missions are launched to the distant reaches of the solar system, our knowledge of these faraway bodies will continue to expand. This growing body of knowledge may one day allow us to make even more accurate predictions about the future of Pluto and its interactions with Neptune. Pluto's orbit also offers valuable insights into the early history of the solar system. The highly eccentric orbits of objects in the Kuiper belt, of which Pluto is a part, can be linked to the process of planetary migration that occurred billions of years ago. During this period, the giant planets, particularly Jupiter and Saturn, moved inward and outward, disrupting the orbits of smaller bodies in the outer solar system. This may have contributed to the current structure of the Kuiper belt, including Pluto's peculiar path. By studying Pluto and its interactions with Neptune, scientists can learn about the early dynamics of the solar system, shedding light on how it evolved into its present state. Ultimately, exploring the potential for future disturbances to Pluto's orbit is a fascinating avenue of study. While the current stability of Pluto's orbit is reassuring, it's important to remember that the solar system is a dynamic and ever-changing environment. New objects, such as those in the Oort cloud, could potentially perturb Pluto's orbit in the distant future, and the movements of the gas giants could shift in ways that alter the gravitational landscape. Although the chance of a collision between Pluto and Neptune is very low, it's not entirely impossible that some unexpected gravitational interaction could occur. These possibilities highlight that studying Pluto isn't just about understanding one small planet, but about comprehending the broader processes that govern the motion of all celestial bodies in the solar system.